Why do volcanoes erupt at all? If Earth is solid rock, how does liquid magma build up, break through, and turn a mountain into a pressure-driven fountain of fire? This fundamental geological process shapes our planet, and understanding it reveals the dynamic forces at play beneath our feet. The short answer is that heat melts rock into magma. Gases dissolved in that magma build immense pressure, and plate tectonics create the necessary pathways to the surface for these eruptions to occur. This intricate interplay of forces is what drives volcanic activity. When the internal pressure within the magma chamber exceeds the strength of the surrounding rock, the entire system fails catastrophically. It's much like a shaken soda can finally popping its top, releasing its contents with explosive force. This sudden release is what we witness as a volcanic eruption. Magma forms deep within the Earth when solid mantle rock crosses its melting point. This critical transformation can happen in three primary ways, each driven by different geological conditions. Understanding these mechanisms is key to comprehending volcanic origins. First, decompression melting occurs as mantle material rises at divergent plate boundaries. As this rock ascends, the pressure on it drops significantly, causing it to melt even without a substantial increase in temperature. This process is fundamental to the creation of new oceanic crust. Second, flux melting takes place at subduction zones. Here, water released from the sinking oceanic slab lowers the melting temperature of the overlying mantle rock, creating volatile-rich magmas. This addition of water is a crucial factor in generating the explosive volcanoes found in these regions. Third, hotspots are areas where mantle plumes deliver extra heat from deep within Earth's interior. These plumes cause localized melting of rock, even far from plate edges, leading to the formation of volcanoes like those in the Hawaiian island chain. This mechanism demonstrates that not all volcanic activity is directly tied to plate boundaries. How violently a volcano erupts hinges critically on two main factors: magma viscosity and gas content. Basaltic magma, for instance, is low in silica, which makes it very fluid and allows dissolved gases to escape easily. This characteristic favors gentle, effusive eruptions, where lava flows rather than explodes. In contrast, andesitic and rhyolitic magmas are much richer in silica, making them thick and sticky. This high viscosity effectively traps gas bubbles within the magma. As more gas exhales and becomes trapped, the internal pressure builds to extreme levels until the surrounding rock fractures, leading to a sudden and often explosive eruption. At hotspots like those found in Hawaii, the prevalence of low-viscosity basaltic magma leads to the formation of wide, gently sloping shield volcanoes. These volcanoes are characterized by effusive eruptions that produce extensive, flowing rivers of lava, gradually building up their broad, shield-like shape over time. Conversely, at convergent margins, such as those in Japan, the Andes, and the Mediterranean, water-rich and silica-richer magmas are common. These magmas feed steep stratovolcanoes, where pressure can accumulate significantly. This often results in eruptions that discharge in sudden, powerful bursts, creating the iconic conical shapes of these volcanoes. Divergent ridges, primarily located undersea, are sites where new crust is continuously built. These regions mostly experience effusive eruptions beneath the ocean surface, where molten rock emerges from fissures on the seafloor. This ongoing process of seafloor spreading is a fundamental aspect of plate tectonics. Volcanic eruptions span a wide spectrum of styles, from gentle to extremely violent. Effusive Hawaiian and Strombolian styles are characterized by spectacular lava fountains and flowing lava, where gas bubbles burst rhythmically, creating mesmerizing displays of molten rock. These eruptions are generally less hazardous to human life due to their predictable nature. On the more explosive end of the spectrum, Vulcanian and Plinian eruptions are known for their immense power. These events propel towering ash columns tens of kilometers high into the atmosphere, often reaching the stratosphere. Plinian eruptions, in particular, are among the most powerful and destructive volcanic events, capable of altering global weather patterns. Scientists rank the size and intensity of eruptions using the Volcanic Explosivity Index, or VI. This scale is logarithmic, meaning each step roughly increases the volume of ejected material tenfold, ranging from small, localized bursts to truly planet-shaping events that can have global consequences. The VEI provides a standardized way to compare volcanic eruptions worldwide. Volcanic hazards are diverse and can pose significant threats. While lava flows can overrun structures, they typically move slowly enough for people to evacuate safely. However, volcanic ash often travels much farther, posing widespread dangers by choking engines, collapsing roofs under its weight, and severely disrupting air travel and infrastructure over vast distances. Among the most lethal volcanic hazards are pyroclastic flows. These are searing avalanches of superheated gas and ash that race down volcanic slopes at incredible speeds, often exceeding 100 kilometers per hour. Their extreme temperatures and destructive force make them virtually unsurvivable for anyone caught in their path. When water mixes with volcanic ash and debris, you get lahars. These cement-like mudflows can surge along river valleys with immense destructive power, often long after an eruption has ended. Lahars can travel many miles from the volcano, burying everything in their path and posing a long-term threat to communities downstream. Before many eruptions, volcanoes often provide subtle warning signs, much like whispers. These include swarms of tiny earthquakes, which indicate magma movement, ground swelling as magma intrudes closer to the surface, and rising emissions of sulfur dioxide gas. Recognizing these precursors is vital for early detection. Advanced networks of seismometers, GPS receivers, satellite radar, and gas sensors are deployed to detect and interpret these subtle whispers. These instruments transform faint signals into critical warnings, buying precious time for authorities to issue alerts, implement closures, and execute evacuation plans, thereby saving lives and mitigating potential damage. In summary, volcanoes erupt when hot. Rising magma and trapped gases encounter fractures opened by the relentless forces of plate tectonics. These eruptions can manifest in various ways, sometimes as gentle, effusive flows, and at other times with explosive, catastrophic force, constantly reshaping our planet's surface. We hope this explanation has shed light on the fascinating and powerful world of volcanoes. Which geological mystery should we tackle next? Earthquakes, tsunamis, or the broader topic of plate tectonics? Tell us your pick and any questions you have in the comments below. Your feedback helps us explore the topics that interest you most.